The proof of the first part of the Borel Cantelli lemma is very straightforward. So you just start with the probability of A star, and you use the definition to write this as the intersection of the union of A sub n's. What you do next is that you want to pull one of the infinite stuff outside of this probability. And remember that this guy is equal to the probability of the limit as n go to infinity of the set's union from n to n to infinity of A sub n's. And this limit exists because this union is a descending sequence of sets as n gets bigger and bigger. And this limit, because of its existence, is same as the lim inf as n go to infinity of the union of those sets. And this is further less than or equal to, let me add a reference. This is the exercise 8 in page 27 of Folland's real analysis, second edition. And again, you know that this lim inf is just same as the limit as n go to infinity of this probability. But by the subadditivity of probability, by the subadditivity of the measures, you have the last term is less or equal to the limit as n go to infinity with the summation from n equal to capital N to infinity of those probabilities. And you know that this sum is the tail sum for this finite sum, which is 0 as n go to infinity by the elementary real analysis. Because this infinite sum is finite, so you get the limit of this tail sum is equal to 0 as capital N go to infinity. And this finishes the proof of the first part. But here, I would like to make a remark that you can get this part from this part immediately by the theorem 1.8 part D of Folland's real analysis, second edition. This is on the page 26. But you would need this P to be a finite measure to get that this part is actually equal to this. Not just less than or equal to. The advantage of our approach here, so the advantage of our approach is that the part 1 of Borel Cantelli lemma holds for any measure P could be infinite measure, even if this measure is not a probability, even if it is an infinite measure, we still have the part 1 of the Borel Cantelli lemma hold. That is why we want to go through several steps for this. The slightly tricky proof will be in the statement 2. Suppose now that the summation of probability is infinity and the events are independent. And you want to prove that the probability of the lim superset is equal to 1. How are we going to do this? Well, in measure theory of probability, so in order to prove something that has full measure, note that in this space, the probability equal to 1 is same as saying that this guy has full measure. In order to prove a statement like this, we usually deal with the complement of this event or variable set. So what we are going to do is that we are going to consider the probability of the complement of this. Okay, so what is the complement? By this definition. By definition, this gives you the following. So instead of taking the union first and followed by intersection, you're going to take the intersection first and then followed by the union. So this is going to be the first to take the intersection and then the union of a sub n complement, and the intersection is from n equal to m to infinity. The union is from m equal to 1 to infinity. Okay, now we want to pull this union outside of this probability. Noticing that this intersection is an ascending sequence. And this probability is equal to the limit when m goes to infinity of the probability of the intersection from n equal to m to infinity of a sub n complement. And let me remind you that this result is the theorem 1.8 part C of full-length serial analysis on page 26, and this is his second edition. If you don't remember this result, you just look it up. And this is true even if the p is any measure, not just a probability measure. So this is not the place where we are using the fact that p is a probability measure. We will use the fact that p is a probability measure later, but not here. So let's continue with this. This guy is equal to the limit as m go to infinity. Now we want to do something on this infinity here. This part, by measure theory, is equal to the limit as capital N go to infinity of the probability of the intersection from n equal to m to capital N of a sub n complement. This intersection gets smaller and smaller as capital N goes bigger and bigger. And this part is equal to this limit because of the theorem 1.a part D of Steele-Follans real analysis, second edition on page 26. So here we are really using the fact that P is a probability measure. Actually, we are using that it is a finite measure in here. Because P is finite, you have the continuity from, this is called the continuity from above, which uses the finiteness of the measure. So I should emphasize that we need P is finite in here. And now let's continue. So we've got two limits, and the thing we care about is the probability of this intersection of the complement of A sub n. And this is equal to the product from n equal to m to capital N of the probability of A in complement. Here, we are using the independence of the events A sub n. Remember by probability theory that if A sub n's are independent, then their complements are also independent. And that was proved by induction. It shouldn't be hard for you to check. And this is equal to the product from n equal to m to capital N of 1 minus P of A sub n. Here, we are literally using that P is a probability measure. Otherwise, we cannot write this as 1 minus something. So why is this 1 so important in here? It won't be so great this 1 is replaced by some other numbers, like 2 or 3. And here's why. Some people may remember that in elementary real analysis, there's a result about the convergence of infinite product, which says the product like this converges if and only if the summation of this part is finite. Now you get a divergent summation. So you will get a divergent infinite product. There are two cases for an infinite product to be divergent. First, it could be divergent in the normal sense, that it could be very wild. It can be anything as capital N goes to infinity. Another situation for divergence is that it's the so-called divergent to zero, namely this limit as capital N goes to infinity will be 0, but in that case we call it divergent instead of convergent. But some of you may not remember the result at this point, so let me write this down carefully in details. So this will be, so we'll copy the limit above down in here, and this is the limit as capital N goes to infinity. Now we'll play a small trick over here. So products are hard to deal with. So instead, we're going to turn this into the summation. How do you turn a product into summation? The common trick will be you consider the logarithm. So what we are going to do is that we are going to take the log of this followed by the exponential function. Now here's the interesting part. We get this logarithm. The natural approach will be to break this down into summation from n equal to m to capital N of the log of 1 minus p of a sub n. So this is equal to this. And this part, we're going to apply an inequality for this part. Log of 1 minus something is less than negative of this. So this part follows from an inequality from calculus. Log of 1 minus x is less than or equal to negative x for x in the interval from 0 to 1. When x is equal to 1, you should understand the left-hand side as the negative infinity. So now you just copy all the rest down in here. So in the end, you will get lim, and the expectation of negative, the sum from n equal to m to capital N of this probability. Taking the summation. Now, because the exponentials are continuous, now you can move this n equal to infinity inside in here. And remember that this summation is equal to infinity. So this sum will be infinity. In the end, you're going to take the exponential of negative infinity, which is just 0. So what we have proved is the complement of A star has probability equal to 0. That means the probability of A star is equal to 1. And that finishes the proof.